Swayam Prabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The topic of today's session is NFV and SDN. NFV stands for Network Function Virtualization, and SDN stands for Software Defined Network. Gets started with software defined network, SDN. So, SDNs are designed as a new intelligent architecture to reduce the hardware limitations to make the networks more flexible and agile. Meaning to say that here the main idea of SDN is to separate the control and data plane and enable the external control of the data through the logical software component that is called controller. And SDN is based on three principles. One is the decoupling of traffic forwarding and processing from control. Second is logically centralized control. Third one is programmability of network services. Let us summarize this particular idea of software defined networks. Now, you can see the networks, normally they are called traditional networks, which comprises of switches, routers, hubs. They are called the active or a passive or active network elements. Now, these particular routers, switches are, let us say that they form the network topologies. Let us say that this particular switch is connected in this particular way. So, you can see that these components, whether they are active components, active network components, they are either called passive network or they are called switch, routers and hubs. They will form the network. The idea of this network is that packets which are originated by the applications, they are to be transported over this particular network. So, this network transports the packets from source to destination through different hops, and these hops are forwarding elements, whether it is a switch, router and so on. Through forwarding nodes, they are either the switch or the router, etc. Now, the question is that this particular network has both these devices are having these particular devices have both hardware plus software within it. Now, that means this software is the control and the hardware is the data plane or forwarding node. So, the control and forwarding, everything is embedded in all these devices, and this is all pre-configured. So, the network traffic which will be passed through, which will be passing through this one, is already embedded its control within these particular devices, and it is not programmable thereafter. So, flexibility is not there. That means, if let us say that you want to divert the traffic, or you want to divert the traffic to get more bandwidth and prioritize that traffic, those kind of issues are not there, and that is called traffic engineering. Traffic engineering is not possible in the traditional network. So, what has been thought of a software defined network? This software defined network will then will divide this control and data plane separately. That means, the control part will be taken away from all these elements and will become a separate entity in software defined network, and they will become only the data plane, that is the forwarding of the data. So, this becomes the control plane, and this concept is shown over here. So, that means, the control is taken away from these particular devices, and these devices will become only the data forwarding devices without without the control embedded in it. Control is separated out, and that is called the control layer, and remaining part, that is forwarding plane, will be called the data plane here in this case, and this is called the software defined network architecture. Now, what is the advantage is that this is a centralized control. So, here you can program the entire network. So, entire network can be programmable. So, if the entire network is programmable, that means you can perform various traffic engineering depending upon the applications which are running over there. So, if it is a data center network, or it is the geo distributed data center network, or it is appearing on inside the data center or outside the data center, if this is applying the principle of software defined network, the entire network can be programmable for better efficiency and the requirement of quality of service by the applications. So, let us see again under this perspective the software defined networks. So, software defined networks are designed as the new intelligent architecture to reduce the hardware limitations and make the network more flexible and agile. So, once you say that the intelligence, or that is programmability of the network, is separated out, then in that case this particular hardware is no longer limitation, but it can be programmed. So, you have to just change the program, that is called control plane, or the control you have to change, and you can make a network in a new with a new functionality, more flexible and agile. Agile means quickly you can program and build a new network. Other than earlier days, you have to replace the entire these set of equipment for any change in the architecture, and that is now being eliminated over this particular concept called software defined network. So, again let us say that the main idea in software defined network is to separate the control and data plane and enable the external control of the data through the logical software component called the controller. So, therefore, the external control of the data is done through a piece of software, and that is called a controller, and this controller has the capability to make the programmability of this entire network. Therefore, software defined networks is based on three architectural principles. First is to decouple of the traffic forwarding and processing from the control. Earlier it was done in the same element, that is the active network element, that is whether it is a switch, whether it is a router, all the logic, that is the control and forwarding, was embedded in those kind of devices. Now, this particular software defined network will decouple this forwarding and the control. Therefore, the hardware and software both are disintegrated, or they are made independent, and allow this independent deployment of the control in the control plane and the data forwarding into the data plane, and therefore, processing element will become commodity machines and it is not the vendor specific configurations. Second important architectural principle of software defined network is that the logically centralized control it will give in the control plane. So, that means a centralized SDN controller can orchestrate the resources that spans a number of subordinate entities and better abstraction to its clients. So, that is what is shown here in this particular viewpoint. Third important thing is programmability of network services. Now, to permit the clients exchange information with the software defined controller, which results in an agile network. What do you mean by the agile network? Means your network can quickly be rebuilt, programmed, and can be applied for, can be used for different applications. Now, let us see these more details, some more terminologies which are there. So, here the application layer will generate based on that network part of that application will generate the traffic, and the traffic will be injected here in this particular network for the transportation. That traffic will use the northbound interface. So, they are called northbound traffic. So, northbound traffic will inject the traffic for transportation into the network. Now, coming to the software defined network, now it has two parts, that is the control plane will now interact with this northbound interface, that is northbound traffic requires the intervention of the control plane. Now, control plane will use the network services and will then inject the southbound through the southbound interface the traffic to be flown in the data plane, that is the infrastructure. So, therefore, this control plane has two interfaces, one with the application interfaces, that is accepting the northbound traffic through the northbound interface, and then it has another interface with the data plane. So, the data plane using southbound interface, or it is also called the open flow switch. Now, it will then use the infrastructure layer, that is the data plane, and here in the data plane the data or the packets will flow from source to the destination through different hop. So, how this particular data will flow, which path to be followed, that instruction or the program or this instruction will come from the control plane, that is. So, therefore, this particular programmability, how the data will flow into the data plane, is normally programmed with the help of control plane, and therefore, this particular aspect is being passed to the application layer for ensuring the quality of service, and also the network can be agile. So, that it can be programmed to ensure the quality of service by this particular network. So, this way the network will become programmable. So, software defined network will make this network as programmable. So, this is called the programmability of network services, that is done at the control plane, or you can say that this is to be done by the controller, that is called SDN controller, and this control is locally, that is centralized control, in the sense it can be programmed at one place and is being affected at all the devices, that is the active devices of the network, that becomes the transport layer, or it is called the data plane in this terminology. Now, let us see that these particular main SDN architectural components are the resources and the controller. So, the resource can be anything that can be utilized to provide the services in response to the client request, like network functions, physical or the virtualized, and the controller is logically centralized entity instantiated in the control plane, which runtime operates SDN resources to deliver the services in the optimal manner. So, therefore, this controller is the logical entity, and this gives the instructions to all the data plane entities. So, this is shown over here, that is the control plane versus data plane. Here the control plane in this particular transport or in the network, control plane is used to exchange the signaling messages in order to control the user equipment data session. For example, there is a data session of the user equipment. So, that means user equipment is, let us say, a mobile phone. If it generates information to be passed on to a public distribution network, it has to go through the network. Now, this particular application will have two parts. One is the control part. So, the control packet will flow through this particular orange part. So, you can see that the control plane is the signaling part, that is shown over here. This becomes the control plane messages. So, control plane messages, that means user has to first interact with ENB, and ENB is MME, mobility management, and then entity, and then home service subscriber, then HSS. So, this HSS MME will authenticate this user whether he is allowed to use this public network, that is LTE network or is 4G network. If it is, then it will allow all these particular ENB to forward its packet, and this forward packet will be done through ENB to service gateway, and a packet gateway network will then be enabled to send the packet of this particular. So, therefore, the user plane used to exchange the user data. So, you can see that the orange line is nothing but the user data, but to accommodate this user data in the network, it has to have the permissions, requisite permissions, and this will be handled with the help of the control plane. So, control plane and data plane separation will make this particular network more programmable and easy to run here in this case. So, software defined network will manages the control plane here in this case, that is SDN will manage the control plane, and its duty is to communicate the application or the client entities in general and the data plane. So, the network infrastructure remains ubiquitous to the application. The software defined network is responsible for virtualizing and orchestrating the underlying resources. So, this also plays an important part in orchestrating and the underlying resources to be allocated for different applications based on the different requirements. So, that instruction will come from software defined network controller. Now, controller virtualization function refers to the aggregation and abstraction of the underlying resources it manages. So, these virtual resources can be statically configured by the administrator or allocated dynamically as needed. Now, there is another complementary aspect, that is called network function virtualization. Meaning to say that all the network equipments are virtualized, and they will run as the virtual network functions. That means, in the form of the software and no longer is specialized So, let us see the network function virtualization. Network function virtualization avoids the need for specific hardware for each network function. For example, why we require a separate entity for router, switch or hub or any other devices that we have seen, let us say that HSS or MME, all these why separate equipments are needed. So, specialized hardwares are now not required with the help of virtualization technologies, which is very much we have seen in the cloud computing. So, in the network area, when we virtualize, that is called network function virtualization and no longer be required to be operated as a specialized hardware. So, therefore, a commodity hardware that is called the data plane will good enough to have this kind of functionality embedded with the help of the virtualization, which is nothing but the virtualization that is hypervisor layer, and then these particular functions will be running on the virtual machines. Therefore, these particular specialized functions or a network devices becomes the software entity and therefore, very easy to manage and they become quite agile. So, therefore, this network function virtualization with this new technology in the network is becoming more agile, scalable and easier to implement. The 5G, that is 5th generation network, takes the advantage of this virtualization approach to achieve the greater bandwidth, high density of the connected devices, low latency to provide the service to these categories of service. Therefore, they are called ultra reliable low latency communication, that is URLLC, and such communications, such services are used for the applications such as self driving cars, mission critical broadband or internet automation. The other type of services is called massive connectivity to support massive internet of things, and then enhanced mobile broadband, that is the capacity enhancement for 3D and 4D video streaming or working and playing in the cloud. So, software defined network, if you see in perspective, it works on 3 different principles: virtualization, softwareization and orchestration. So, let us see in the perspective of LTE system. LTE system, you know that the full form of LTE is long term evolution. This is nothing but a 4G cellular system. So, the 3GPP long term evolution, that is LTE program, has its own set of goals and requirement and beyond the basic principles of 4G. So, 3GPP is in charge of establishing the suitable LTE standard in order to achieve the necessary goals. So, there are 3 areas of 3GPP which focuses on, that is called evolved universal terrestrial radio access, that is E ultra. That is, here the interfaces is based on OFDM network layer, uses MIMO techniques to increase further data rates. Second area of 3GPP is evolved universal terrestrial radio access networks, that is EUT-RAN, and then like UMTS access network. The EUT-RAN has only one node, that is called evolve B node or ENB, it is called evolve node B. Third one is called evolved packet core or EPC. In LTE, the network is greatly simplified as an IP based network, replacing the 3G network component with mobility management entities, MMEs, serving gateways, that is SGWs, and packet data network, that is P gateways. So, that is all is explained over here. So, it is, you can see that evolved node B, that is in UT-RAN, we are going to see, that is it has E node Bs are there into it. So, UT-RAN has a simplified architecture and comprises of evolved node B, that is E and Bs. Whereas, EPC is concerned, that is called evolved packet core. So, in EPC you can see that it is a simplified architecture which is support an IP based services. So, it has an MME, that is a mobility management entities, mobility management entity, then evolved packet core, and this is service gateway, or a serving gateway, and this is called a packet data network gateway, packet data network gateway. So, this is an LTE system, and you can see that U ultra, that is evolved universal terrestrial radio access, that is an air interface which is based on OFDM and MIMO technique to increase the further data rates. So, your user equipment now using that E ultra, now it will have the air interfaces which connects through to the user equipment to the ENBs, and ENBs are now then connected with the evolved packet core, and evolved packet core has these elements to accommodate both the control and the data plane of this particular LTE system. Now, let us see in more detail about all of this, that is UTRAN. If we see, so the main difference between UTRAN and any other 3G system is the absence of radio network controller. So, UTRAN, that is E node B, is the only node in UTRAN, and the traditional functionality of radio network controller has been shifted to ENBs. So, every type of information exchange in UTRAN is carried out through an IP packet, which is solely an IP based network. So, you can see that LTE is an IP based network now. So, the primary difference between UTRAN and EUTRAN is the absence of RNC, that is the radio network, that is there is no radio network controller. Network controller is not required in this case. The functionality of RNC has been now shifted to ENBs. Enhanced node B. So, you can see here in LTE radio network, that is EUTRAN. So, what you can see over here is that in EUTRAN you have an ENBs and you have different type of interfaces, that is X2 interface and UU interface, S1U interface and S1 MME interface, and these ENBs are now able to have this connectivity with the user equipment, and there is no radio controller, radio network controller is needed, and all the functionalities is now embedded here in E node B, and this becomes a perfect IP based network. Now, let us see about LTE system, that is E node B. So, as I told you that radio network control function has been transferred to E node B, that is enhanced node B. So, enhanced node B carries out the following task: radio resource management is now the task of E node B, then IP header compression and encryption of the user data stream, then uplink and downlink radio resource allocation in both uplink and downlink, then transfer of paging messages and broadcast information over the air, selection of MME when the user equipment attaches to the network, and handover mechanisms when the user equipment moves from one ENB to another ENB, all are the functionalities of E node B. Now, let us see the core, that is enhanced packet core, that is an LT system. So, the entities in EPC include the mobility management, that is entity, that is MME, serving gateway, packet data network gateway, that is PGW, and evolved data gateway, that is EPDG. So, the main difference between 3G core and the EPC is that EPC is only for the packet data services, and there is no dedicated core network for the voice services, that is it is purely an IP based network. So, EPC is wholly an IP based network where all the information exchanges are through an IP packet. Now, let us see about the MME, that is mobility management entity in LTE system. So, mobility management entity here has taken on the management of user equipments, it is registering with MME. In order to authenticate the user equipment, the MME collaborates with HSS and the UE. It also in charge of initiating the data session for the user. So, the main functionalities of MME are managing and storing the user equipment context, generating the temporary identifiers for user equipments, ideal state mobility control, distributed paging messages, security control, roaming, authentication, and bearer control. So, all these are the functionalities of mobility management entity. Now, then serving gateway, there are two gateways in enhanced packet core, one facing towards the external packet data network, that is P gateway, packet gateway, and the other is facing towards UTRAN, that is service gateway. So, you can see that both are over here, one is facing towards UTRAN. So, that is called the serving gateway, the other is called facing towards the packet data network called P gateway. So, a user equipment may connect to only one service gateway, serving gateway, but it may use multiple packet gateways. So, serving gateway is fundamentally an IP packet router with some added functionalities. So, serving gateway has a control plane interface with MME and packet gateways and the user plane interfaces to ENB and packet gateway. So, the functions of serving gateways are as follows. So, it anchoring the user plane for inter ENB handover, anchoring the user plane for inter 3GPP mobility, similar to SG and SN in a pre LT 3GPP network, anchoring like GGSN and packet routing and forwarding. Now, let us see about PDN gateway. So, PDN gateway or PGW is similar to the GGSN in UMTS or HA in NMIP, is the gateway between the LT evolved packet core and the packet data network. So, packet gateways are primarily the IP packet router with some specialized functions. They are both control plane and the user plane interfaces between P gateway and S gateways. So, P gateways host the following function: assist the user equipment with the packet routing and connectivity to the packet public distribution network, allocation of IP addresses to user equipment, accounting and quality of service such as per user based packet filtering, transport level packet marking based on QoS parameter, rate enforcement and charging. So, anchoring or the user plane for the mobility during the inter MME and serving gateway handovers, LTE and preliminary 8 3GPP handovers and 3GPP and non 3GPP handovers. Now, let us see about HSS. that is home subscriber server HSS. Home subscriber server has the master database, it stores the user subscription information, identification, service profile and location, and generates the security related information. Now, it is a database for user identification, numbering, service profile. It is primarily involved the user authentication and authorization. So, HSS generates the security information for mutual authentication and integrity check. Ciphering can provide the information about the user's physical location, can have more than one HSS in a home network depending upon the network of mobile subscriber and the equipment capacity. So, here you can see the location of HSS shown over here. Now, let us see about 5G. So, these services, 3 services grades are allowed in 5G, that is enhanced mobile broadband, second is massive machine type communication, third is ultra reliable low latency communication. Many new technologies have been enabler of the 5G groundbreaking approach to the network architecture, and virtualization allows move traditionally the core network element from dedicated hardware to the virtualized network resources such as virtual machines or the containers. So, 3GPP specifies LTE access support to the new 5G architecture, and there are 2 variants of combining LTE and the new 5G radio access called NR, new radio, non standalone architecture and the standalone architecture. So, they are shown here in this particular figure that all these details, but let us understand about 3 different services which is being graded in 5G, that is called enhanced mobile broadband to serve more densely populated metropolitan centers with a downlink speed approaches 1 Gbps indoor and 300 Mbps for an outdoor speed. Massive machine type communication MMTC to enable the machine to machine communication and Internet of Things application, ultra reliable and low latency communication to address the critical needs of communication where the bandwidth is not important as the speed, and the aim is to achieve an end to end latency of 1 millisecond or less. So, many applications have been here being enabled. So, let us see about the separation of data plane and the user plane here in this particular scenario. So, let us see that evolved packet core. So, you can see that here between LT and EPC you have seen that it uses the virtualization technique or a software defined network technique. In this case you can see that user plane, this is the user plane and this is the data plane, this is the control plane between LT and EPC. Now, new radio, that is new 5G radio, here you can see that in that case also it divides into the user plane and the data plane. And here you can see that enhanced LT will have also both the things. Now, this new radio and LT both are combined in 5G, that is shown over here. Now, 5G faces many challenges, one of them being to support a wide variety of business models, enabling multiple use cases and multi vendor integration. Now, network slicing is the driver to achieve this, and since it allows to create different separate logical networks over the same physical infrastructure. So, 5G also aims to provide the flexible with service demands, adapt in the real time to the dynamic traffic changes and manage the network connectivity, for which software defined network and NFVs are essential. So, NFV decouples the network functions from the proprietary dedicated equipment, optimizing the network resources and making the network easily scalable. So, all these things are explained over here. Let us see that it is the traditional network. So, in this traditional network you can see that all these devices are available for running the specialized services. For example, E and B will be a separate hardware for SG gateway and GGSN, DPIP gateway, DNS, MME, HSS, OCF, they are all different equipments, and together you require different vendors to supply them here in this case. So, the deployment here the specialized equipments are there, that is purpose built equipments are there, that each equipment is now taking care of specialized services. Whereas, using network function virtualization, this particular is there is a separation of specialized, there is no need of specialized equipment. Here in this case the devices are virtualized, that is the services or the functions are called now network function, and this is called network function virtualization. So, virtual network functions will run on any commodity hardware, therefore, they are not required to be specialized appliances or purpose built equipment for that, and this will ensure these following advantages: that network function virtualization decouples the network functions from proprietary dedicated equipment, optimizing the resources and making the new network easily scalable. Now, let us see about the NFV in more detail. So, NFV brings many benefits to the network operator, that is reduced equipment cost and reduced power consumption, increased velocity time to market by enabling the operator to reduce the maturation cycle, the possibility of running the production, test and reference facilities, reducing the development cost, supporting the multi-tenancy, then supporting optimizing the network configuration, traffic patterns and service demand, reduced energy consumption, server storage as well as workload consolidation and the location optimization. Now, to do this, let us see about the NFV architecture. Now, this NFV architecture is also governed through the standards which was made available with the help of several consortium companies. They joined together, and in IIT they have made a reference architecture for NFV. So, that is what is presented over here. So, in NFV architecture you have now following components. One component which is shown over here in a blue box, this is called network function virtualization infrastructure, NFVI. The other is in yellow box, that is called virtualized network functions, and third one is called NFV management and orchestration. Now, when we see each and every one, each one of them individually, why they are required. So, the NFV management and orchestration is the control entity or is the central entity that is very much needed to realize this NFV in the NFV architecture. The second one is called virtualized network functions. As I told you that this will decouple the hardware and software, and all the specialized functions will become the virtual network functions, and these virtual network functions will run on the virtual machines. Now, these particular virtual machines are nothing but they are providing virtual compute, virtual storage and virtual network to run these virtualized network functions. For that it requires NFV infrastructure. So, NFV infrastructure is being provided with the help of a hypervisor, that is a virtualization layer, and this virtualization is done for the hardware resources, that is the compute, storage and network are now virtualized, and they will become the virtual compute, virtual storage, and they are being provided in the form of virtual machines. So, NFV infrastructure provides the virtual machines, and on top of it these virtual machines, these virtualized network functions will run, and all of them will be orchestrated or managed by NFV management and orchestration here in this case. So, let us see about the high level NFV framework is divided into three different domains. As I told you, the first one is called network function, virtualized network function. So, here you can see that it is virtualized network function. What do you mean by that? So, instead of having the specialized hardware, now these virtualized network function will be in the form of virtual SMC, virtual MSC, virtual HLR, virtual SGSN, virtual GGSN. So, these particular virtualized network functions will run as the services, not as a specialized hardware. So, therefore, these particular specialized services, that is virtual network functions, when they will run as virtual MSC or virtual SMSC or virtual HLR or virtual SGN or virtual GGSN, they require the virtual machines. So, these virtual machines will be now running these virtual network functions in this architecture, and this is called NFV, network function virtualization, NFV. So, this is most important component. So, virtualized network function as the software implementation of the network function, which is capable of running over NFVI. Now, network function virtualization infrastructure, that is NFVI, provides this virtual machine support to run these virtual network functions, include diversity of the physical resources and how these can be virtualized. Third important thing is the NFV functions virtualization management and orchestration, that is NFV MANO, which covers the orchestration and the life cycle management of physical and the software resources that support the infrastructure virtualization and life cycle management of VNFs. Now, let us see about the network function virtualization infrastructure, NFVI. So, the role of this layer is to host the hardware and manage the physical part. So, here this is what we are talking about, NFVI. So, the physical part may be that the servers from various companies which has the CPU, memory and the network within it. On top of it, a virtualization layer will run, and this will provide the virtual resources, and this is called NFVI. So, NFVI, now requirement of NFVI or control is done through the part of NFV management layer, that is called VIM, that is virtualized infrastructure manager. So, virtualized infrastructure manager will give the requirement or will manage the life cycle of these virtual resources. The second important component here is called virtualization layer, which is also called the hypervisor. This layer also contains the critical component, by name it is called hypervisor, which is responsible for abstracting the physical resources into the virtual resources. The virtualization layer sits just above the hardware that I told you and abstract the resources, so that it can logically be partitioned and provided to VNFs. Here you can see that performing their specific network function. Now, coming to the virtualized infrastructure manager, that is VIM. So, on the right side there is another component by the name called VIM, that is virtualized infrastructure manager, which is a part of NFV management and orchestration. So, the role of VIM is to management and control the NFVI. So, VIM also manages FCAPs, reports and events of these NFVI. So, here we are going to, let us say, discuss about the virtualized infrastructure manager, that is VIM. It deals with the management and control for NFVI. So, this is NFVI, and this VIM does this management and control of NFVI, also manages the reports and events in this architecture. And NFVI is a network function virtualization infrastructure. It manages the physical part in the NFV, and also it has the hypervisor, which is responsible for abstracting the physical resources into the virtual resources. Now, the next important part is virtual network function. So, VNF, that is a VNF on the other hand is a network function using the software that is decoupled from the underlying hardware. So, these virtualized network functions runs inside the virtual machines and are known as virtual network functions. So, as I told you that you can see from here these virtual network functions will run on virtual machines. So, virtual machines, it may be it runs on 2 virtual machines, or it may run on 1 virtual machine, or it may run on 3 VMs, or it may run on 1 VM, or it may run on 2 VMs. So, it depends upon NFVI, it will provide how many virtual machines are needed to run these virtual network functions. So, virtual network functions is the network function using the software, and therefore, it uses the virtual machines to run, and these virtual machines are being provided by the below layer, that is NFVI. So, these virtual network functions are now managed with the help of VNF manager. So, VNF managers will manage the life cycle of virtual network functions, setting up, maintaining, tearing down, and FCAPS virtualization and VNF architecture. Now, VNFs are the basic block of NFV architecture. For example, it is virtual IMS, virtual MME, virtual MSC, virtual switch, or a virtual router. So, all these different devices functionalities are being run as the network function or as the software. Now, element management, that is EM, the FCAPS and OMs of the applications such as VMSC or VSMSC or VHLR is done by the element management as shown over here. This is called element management. So, element management and does the FCAPS of the application such as MSC link down, MSC KPI degradation, and so on. So, EM we have shown that it is an FCAPS of the application such as link down, KPI degradation, etc. Now, FCAPS is an acronym for fault configuration, accounting, performance, and security. Fault configuration, accounting, performance, and security called FCAPS. The management categories is this is the complete operation, maintenance, and life cycle of any telecom node. So, EMs, so FCAPS layers are as follows. So, it starts with virtualization infrastructure manager, then virtualization network function manager, then element manager. So, all these things are the part of FCAPS. So, FCAPS of NFVI, that is VM and hardware, is done by VM, that is virtualized infrastructure manager. FCAPS of VNF here is done by VNF manager. VNF full form is virtual network function. So, FCAPS of telecom virtualized applications such as VMSC and VHLR is done by element manager. Now, coming to the software defined network, after having understood that NFV deals with the agility and making this particular network establishing in a very quick manner in a few seconds, that is being provided with the help of NFV, and NFV with the help of virtual compute, it will give the new services or the nodes. Now, how about the transport part or the network reachability in the sense of IP allocation, policy, opening, routing changes, bandwidth, end to end reachability, and service testing. This is done with the help of software defined network. So, software defined network changes how the network is fundamentally done. And instead of having the network intelligence distributed across every device, SDN aims to centralize the command and control in a master device and to split the networking into 3 phases, that is data or the control plane, control data or the forwarding plane and the control plane and the management plane in SDN. So, SDN in SDN NFV helps in virtualizing the network, which helps us in rapid deployment and ultimately reduces the new service and new node creation in few seconds, but in the problem of network connectivity where we need the multiple things such as IP allocation, bandwidth, policy opening, routing and so on and so forth. All of this is not automated and takes a lot of time in this case. So, the typical scenarios is that to do this in a traditional network is very consuming. So, SDN helps us by making this routing switching network flexible and programmable. So, therefore, software defined network what it does is will separate the data plane and the control plane. So, control plane will become the brain and the data plane it will separate. So, in the traditional network, the role of the control plane to take the routing decision, every router has its own brain to decide the best path to route. These routing decisions are taken on the basis of the route configured in the router and routes learned from these adjacent node. Now, software defined network in the traditional network, it is used for performing the operation maintenance of the network. So, software defined network will have the separation of control and the data plane. So, the controller, you can see that the control part from all the devices is separated out in a form of a controller, and rest are all with the data plane, that is forwarding function is with the data plane. Now, this is an emerging architecture of the network that is fully programmable, dynamic, manageable, cost effective and made it clear for dynamic and random requirement. So, in SDN architecture, let us see that the open flow protocol is the key. So, open flow here we are showing you is the key to the entire topology. The groups of few started working on the open flow standard. So, open flow open networking foundation, also called ONF, to promote SDN and open flow. So, let us see some more part of this particular SDN architecture with the help of open flow. So, you know that SDN framework separates the control and the data plane. So, data plane will become the infrastructure layer where network devices are there as the forwarding part of this, and using open flow it will have the interface with the SDN controller, and it will then manage these devices which are called forwarding devices. So, open flow standard, you know that it has the control plane interface, and the SDN control software based on the application interface or APIs will now direct what kind of services are required from the transport or forwarding, and open flow is one such important protocol in SDN for running this particular topology. So, conclusion, in this lecture we have discussed the need for software defined network, that is the key ideas and challenges of the software defined network. This makes the network programmable. The second important part is called the network function virtualization, and this allows that even commodity hardware can be used, that is not required the specialized hardwares for different functions, for different network functions such as routers, switch, HLR and so on. So, therefore, this is done with the help of virtualization, and whereas software defined network divides the control plane and the data plane. is based on this technique of control plane. So, we have also seen the components of 5G, LTE and 5G systems. So, in the next lecture we will discuss more details of how this NFV and SDN is going to be useful for realizing the edge computing or the cloud and edge computing system, where these networks are very much useful. We are concluding this particular lecture. Thank you.